Hello everyone, welcome back to the Exploring Machine Intelligence class, or as I would like to also call it, nickname it, the Deep Learning for Artists class. Today's topic will be the basic building blocks of neural networks, and so we will look into what are neurons and how they are connected into larger models. Okay. So to start with a sort of motivation for today, let's look at a very simple neural network model, which is this one, and let's look at it in this interactive visualization. Okay, so if we draw a number here, what happens is that the number is processed as an input here, and then using a neural network, which is something that we will discuss more in detail today, and which is this. This input is processed, so kind of going up in this graph, up into this classification, and it is correctly identifying it as a number 2. So if we try some other numbers, I think 3 or roughly 3 works relatively well. And you can see that this model is relatively robust even to my messed up 3, right? What each of these blocks means, we will kind of discuss today. But roughly speaking, every one of these blocks is a neuron, and all of these lines are its connections. So its connections to the input, its connections to some other neurons, and then its connections to finally the outputs. As you can notice that there is a lot of neurons, and they are always kind of connected to each other in layers. And as you can also see, there are some different activations. So how bright each neuron is firing is how strongly it is reacting to whatever it's seeing. Okay, so this is just a brief motivation at the start of the lecture, because we will go into all of these details and explain what each of these things means actually for us. Okay. All right. Before I go into the class, I would like to stop with the last week's quiz feedback. Okay. So first of all, thanks everyone for filling it out. There was a good amount of feedback from you guys, and what I was quite excited by is that a lot of you are from really different backgrounds. So there are people from animation or game dev or mathematics or interaction design or music productions and illustration, etc., etc. And so there are a lot of different backgrounds, which is really good for the class, I think, and for the possible projects that we can end up doing. So some of you mentioned some topics of interest, so something that you would like to explore in greater detail. So, for example, something like machine learning used in animation or in music generation, etc., etc. And so when we get to the different more complicated models, I will try to include these examples there as well. And there were some kind of more general requests. So some people were saying that they would like to, instead of just reusing some pre-trained models, they would like to learn how to train and create your own models, which is good, because we will start with a simple one today, and later in the year we will also go through training other ones too. So that this will happen for sure. Then manifesting from digital into the real world, so sort of not ending up with just some image or something that is generated in the digital, but then eventually making it into the real world. So, for example, something like plugging in the 3D printing technology to the pipelines that we can use to generate things. And yeah, I agree, that's a really good category. I think when things become tactile, real, something that we can touch, it's more interesting than when it's just some numbers inside a file that you can lose at any moment, right? And finally, some interactivity and also some physical interactivity with these models. So thanks for the feedback. I will try to at least mention some relations to these areas, or also steer it in a way that includes these. Okay, so to start today's class, there will be several topics today. We will be talking about neural networks, which are, this is a simplified graph of a neural network. We will start with artificial neurons. So these are these smaller units that the neural networks are made of. We will explain what these are, and then we will start plugging in some image data. So basically connecting into these two, explaining how we can actually even connect something like an image into this model. And then we will end up with training a neural network model. So we will start with relatively simple models today. We will kind of be adding to that in later classes. Okay, so maybe keeping in mind the metaphor of a black box, also something that we were working with last class in the practical section, is that we have some sort of model here which has some sort of parameters, and then we are feeding it some data on the input and then kind of getting some outputs on the output. And we have a task to find the best possible parameters so that whatever the model is kind of outputting on its own corresponds the best to what we actually want. So what are the labels? So this was nicely visualized with the use of the line, the linear regression model. Basically, the parameters there were the slope and the intersect, and these two kind of defined where the line would be, and so finding the best position for the line was done in a way that it corresponds to whatever the data coming here and getting out here is. So in this case, we had a model which received one number, the x, and outputted one number, the y. Okay, and so today what we will be doing is basically the same thing. Well, except that this thing in the black box will no longer be a simple linear regression model, but a full-on neural network. Okay. So to start, before actually going into what are the neural networks, let's talk about the basic building block, and that is the artificial neuron. We have some kind of intuitive understanding of what a neuron is, because it's something that has been inspired by a real biological neuron in our brain. And so the way how they work is that they have a bunch of connections to other neurons, so these dendrites that are connecting to all other neurons around in the brain tissue. Then there is some sort of cell inside, some soma, which is accumulating all of these signals. And then the signal is kind of somehow processed and then being sent in this axon to some other outputs, right? To some other neurons. There are some details in biology, like the myelin sheath, the stuff which is basically supposed to protect it from firing into other neurons, which we will not have in with our artificial model. There is also a lot of other complexity. For example, I don't think people actually understand exactly how these behave. So there are some reactions between neurons that are not kind of modeled yet. But let's have this as let's say, the starting point. And let's talk about how to kind of describe it mathematically. Well, so in maths, we would like to kind of maybe mark the inputs and the outputs with some numbers or like some letters. Some variables, so we can call these the x1, x2, all the way to xn for all the n connected neurons which are somewhere at the input side. Then soma, we were saying that this is a unit which somehow like processes all the signals that come through and then changes this and then sends it out. So we can mimic this behavior somehow by a function. We will not yet talk about what the function could be, but let's imagine there is a function which can kind of translate and simulate the soma well. And so in the end, we will have some connection to other neurons, and this is many neurons in real life, and we can call this y. Okay. And so if we have this as a biological inspiration of a neuron, and then we can add to the detail that maybe these different connections to different neurons have different strengths. Let's say maybe the lengths of these dendrites are different, or I don't know what's happening there in the biological world, but let's say that they have different strengths to connect to the soma. We can abstract this or simplify this into a model, which is something looking like this. So we again have inputs on this side. We can call them the same way. We have some weights, which somehow corresponds to the strength of how much we care about each of these inputs. We have the same function, and then we have some output. And so when I was saying about the strength of the input and somehow changing it, weighing it, what this means mathematically is actually this. So these inputs are multiplied by whatever the weight of each of these lines of these connections is. So one neuron has kind of that many connections, that many weights, parameters, as it has the connections. Okay, cool. And so what happens here is that all of these get somehow accumulated into the function in the actual soma or the artificial neuron. Okay. So we still somehow in this model need to combine the incoming signals, which in maths this means summing them, and then somehow process them. And then this processing is the function that I was talking about. So this sort of thing which is simulating the neural activity. Okay. Well, so how to read this formula? We basically are adding multiplications between all the inputs and the weights all together. So there is a big summation between all of these input signals. Then we somehow process this, whatever gets out of here, we somehow process it, and the way we do this, at least in the theoretical sense, is using a sigmoid function. And so I will not go into the details of what is a sigmoid function, but let's say it's a function which will kind of plop all the signals in between 0 and 1. So this is called the activation function, and sigmoid is just one possibility. In practice, we have a bunch of other types of functions there as well. But yeah, so this is what happens in an artificial neuron. If we go back slightly and kind of step into the side of thinking about this as a model and having some parameters, what happens there is that all of this is basically frozen. We don't have much control above it, around it. These inputs are whatever the inputs are of the model. What we can change though is these weights. So these are the parameters that we can change of the model. And so for how many inputs we give it, that many parameters we will have. So with input size of n, we will have n parameters, or we can also call them weights. So there is a small detail that sometimes we actually have n plus 1 parameters because one of these is fixed to 1 and added here, but just for a simplification we don't have to relay. It's just a detail. Okay, and so if we step to the kind of a little bit back to see the bigger picture, at the start of this class we had this sort of illustration of having a model where we are feeding some inputs on the one side and then getting some outputs here. And to be honest, we don't really care about what's happening here. We just care about kind of what the parameters are. And so in similar way, we have this model here instead, where this is the function that's happening here, is some function over the sum of its inputs. Well, this is the same kind of formula. If you look at it, actually for like n equals 1, so for just one incoming input, the mathematical formula becomes roughly the same. This is the added parameter from the last slide, so that's just a detail. But one neuron is something similar to a linear regression. But this will get more complicated and more interesting later as well. So it doesn't end on just one neuron. So in order to train a model, which is basically to just make it useful, make it fit on some data, we have to adjust its parameters. So this could be A and B in the case of a line, or this could be all of these WYs, so all of these different strands on this size, on this side. And we change them, adjust them in the way that this model fits the data. And we cannot really end here. As before with the line, we do need a couple of things to make this work. So we need to know actually how to connect data to this model, and we need some measurement of error. So if you remember last class, we were looking at like the distances between the model and the actual predictions of the model, so or what the model was supposed to be telling. So if we have this model, it's telling that the point at this coordinate should be here, but the data is actually here. So the error would be sort of these distances, right? So in this case, we somehow have to also arrive at having an error for this. Okay, so well, let's directly jump into the data that we care about, and that would be images. Well, this is a 8 by 8 pixel image of something, and how to connect it into a model, as we were describing before, is relatively simple. We just flatten it, and that what flattening means is scanning line by line into a vector. So what this means really is just going one line by one line, and then adding these as values into this vector. So 8 by 8 will make up a 46 or 64, 64 pixels long vector. And if we have these 64 inputs, we can connect them to one single neuron as a model, and we will end up with having 64 connections plus the one from before, the bonus one. Okay. This scales. So if we have larger images, and there is an image of 3, so something that we were showing at the start with the interactive visualization of the model, we have much larger amount of data, right? So 28 by 28 is 784, and so this will be flattened the same way, line by line, into this really large vector. However, this really large vector is still connected to the one neuron. There are the same amount of connections here, and then we have just one output. Right. Well, there is still something missing on this image, even though we plugged in some image data, and that is something that we want to have here. So basically, how do we represent the label saying, hey, this is a 3? So we want this prediction, so something that comes out of here, to be really close to this label that we choose. Or if we say some other number, so maybe like letter 9, this should be something else, right? So yeah. We should also talk about how to establish an error. So if we have a model and we are sort of predicting with it some y as an output, and we do have some label. Let's not talk about what the label is, but let's just say that there is some label. We want to see some distance between these 2 points, and then have this as an error. So mathematically, error is sort of like how far off our model is from what we want it to be, and so that would be something like this: prediction minus label. Well, this is simplified, but we can still work with this as an error function. Okay, so the task then becomes to remember the first images with just having a model. This is the reframing of that task into this case. So the task here becomes change the parameters v1 to vn, so all of these numbers, in order so that when you give the model, this thing, the input image here, you get an answer which is really close to the label that you decided for the model, for this image, for this one particular image. So we will get back into this later. If this sounds confusing, don't worry. Okay. We will have a pause now, and just kind of maybe have a think through the pause if everything up until now is clear, or not necessarily everything, but let's say at least the idea of converting some biological neuron into this sort of simplified model. So having an idea of what these connections are, what happens with the inputs and the weights, and then what happens in the function here. Yeah. Okay, let's continue with the slides. Let's start the next section with its comics. So it's a comic called XKCD. They have a lot of them, but some of them are like sort of geeky, nerdy maths jokes, some are computer sciences jokes, and some are actually machine learning jokes as well. So this is your machine learning system. Yep, you pour the data into this big pile of linear algebra, then collect the answers on the other side. What if the answers are wrong? Just stir the pile until they start looking right. So this really connects to the idea of having like a black box here, and then having some data here, and then having some answers here. And so if this thing goes wrong and the answers are wrong, just have some go at this, stir it around, and then try if whatever these answers again, and then see if they get better over time. So that's the joke. So I will have a short recap on what's happening with the neurons. By the way, don't worry if it's if all of this sounds really complicated. You will see on a simple example that it's not that difficult eventually. So what's happening here is that we have a 6 pixels image. Let's say that this is a maybe 2x3 image or something, and then these pixels are how the image was transferred into just a vector, so flattened. Then we are connecting a single neuron model here, and then each of these connections has some sort of weights. So these weights are the number y, the w. And then we have some sort of output of this neuron on the other side. So far, we have just been using this single neuron as an example, but there is no reason why not to have more than just one neurons in the model. And so the way how you would add the second one is basically just add it to the same place here, and then connect all of those connections from the inputs also with the next neuron. And what you can notice is that, just by the way, that these weights are different. So these are unique weights. I named them U1 to U6 to differentiate from W1 to W6. And also note that now we are basically outputting with this model 2 numbers instead of just 1. So the question really is to ask why should we stop there? So instead of having 2 neurons, we can have just like 1 neuron here, all the way up to basically a neuron. So all neurons, as many neurons as we want, and we call this a single layer of neurons. Kind of the thing to note here is that every neuron in this one layer, all of these single neurons are always connected with all possible inputs, right? So everything is connected with everything from the previous sort of layer. So from the previous step. So for this layer, it's connected with all the inputs on this previous one. and the size of the output is depending on how many neurons we chose. So if each of these neurons has one y, so y1, y2, all the way to ya, then if we choose some amount of neurons, we will have that many outputs from this layer, right? And the question still stands, why stop there? Basically, we can add additional layers. So if this was the first layer and the neurons were marked as n, then we can add another layer, and then, I mean, we can just call them m for now, and we can have as many as we want here. The amount of them can be different from the previous layers, right? So every layer can have their own number of neurons, and the same way as in this case, where every neuron was always connected to all possible inputs, in this case, every neuron here will always be connected to all possible inputs from the previous layer. So I guess what the reading in between the lines, what I was not saying here, is that this layer here is connected to the previous layer, but it doesn't have connections to the stuff which has been here, right? So it's not directly accessing the image, it's accessing the image as it was sort of processed by this first layer. So we are differentiating, kind of each layer is doing maybe something different from another, right? And in theory also every neuron has its own weights, so every neuron is allowed to do some sort of different task. Okay, right. And so to clean up the image from this previous figure here, of the previous image illustration here, we don't need to name all of the neurons, we don't need to mark all of the outputs. We can just sort of summarize it by this image, where we have a bunch of layers inside a neuron, basically as many layers as we want, and each one of these layers will have its amount of neurons. Again, basically any amount we want, and this will become our new model. So this model is now called fully connected neural network. So instead of having a single neuron as a model, we now have a neural network, which means that there are a bunch of neurons which are connected in some way together. And fully connected is referring to the way how every neuron in kind of one layer is always connected with all neurons in the previous layer, and also basically connected to all neurons in the later layers, right? Because every neuron here will be again connected with every one of these neurons here. So imagine just the number of connections between all of these neurons. It will be quite a lot. I have added all of them here, but then kind of just skipped all of them here because it would be unreadable. But each of these connections corresponds to a parameter. So what this means is that each of these connections will have to figure out a number, will have to figure out its own strength. And so the way how we can kind of modify how this model behaves, how this neural network, how this fully connected neural network behaves, is that we change these weights inside it. Right, and so this is something that also happens during the training. These weights are adjusted in a way that then it fits from the input side to the output side. Okay, so we have something here, right? We saw it in the previous slides. We have some inputs on the first on the input side, some images, some data. We call this usually X, the data that we feed into the neural network or to the model in general. And then we have some outputs here, and we call them usually Y, and then we call them labels. And so there is a to this inputting image of 3, we have a label saying 3 somehow, and then we have a label saying 9 for something else, right? And this continues. what we have been showing here as the images which we were using in these examples were numbers from the MNIST dataset, which is a dataset of handwritten numbers. So it's pretty large. There is like 70,000 images in there, I think. And then each of these images will be one of these 9 or 10 numbers. So 0, 1, 2, all the way to 9. And each one of these, well, we can call it classes. So all the zeros are the class of zeros. So every one of these letters or numbers, or actually classes, every one of these numbers will have a bunch of samples which are representing it. So we don't have just one sample representing all the 2's. We have a bunch of them. Basically, in the whole dataset of 70,000 images, roughly, we will have some uniform distribution of all of these numbers. Okay, so the resolution of the images inside the MNIST dataset was 28 by 28 pixels, which is something that we have been showing before. And so we have to actually represent these by flattening them. So we have the 28 by 28 image here, and then we flatten it into a vector of all the pixels, 784 pixels in this case. And so similarly, like the way that we just represented the image into a vector, we somehow need to represent the label on the other side, on the output side, into a vector as well. And so because we had a data set with 10 possible classes or 10 possible letters, we can have this vector which represents, which is called one hot vector representation, and label saying 3 will be this vector with all zeros and 1 in the position of a 3. So what this means is that all of these numbers are kind of not supposed to fire in the end, while this one is supposed to be firing at 1 because it's labeled as a output with label 3. So inside this dataset where we have 0 all the way to 9, and these are the different types of classes, let's say, we will have these labels for all of these inputs. So the same way as we had to represent the input by scanning line by line, we sort of have to translate whatever the label here was into a vector of this size, of size 10, with 1 being the activated number inside the vector. And so this really is because we will plug these into the model somehow, and then we want to then be able to get an answer from the model telling us, oh yeah, I think it's 1, but maybe it's also 7, right? So the model will be then outputting some number like here, and then also some number in this position. So we want this model to be able to tell us what it thinks the different classes are for all of these possible numbers, all of these possible classes. Okay, so in this case it was 10 classes, but we can have different data sets with different amounts of classes. So in a data set where there are cats and dogs, there would be just 2 classes, for example, and then we would be differentiating between those 2. Okay, and so we are slowly getting into a moment where it all should fit together, and we have the model somewhere in the middle here. We have some inputs that we flattened on this side, and then we have some labels which we converted to 1 hot vectors on this side, and then the choice of how many layers we use or how many neurons in each layer we use is referred to as choosing the architecture or designing the architecture of the neural network. And there is no clear way how to do it, so you basically just have to try and see whatever works. There is some intuition behind it, but I will get back to that later, I think. And so I think now we are more or less ready to review the same interactive online visualization from the start of this class and basically look at the transformation between the input here using the already trained neural network, which is something that they have here, and then looking at the output. So remember that, oh right, this is wrong. Okay, they're fixed. So remember, well, why this was wrong, because this is a label for 0, this is a label for 1, this is a label for 2, and only this is a label for 3. So remember that when feeding in this sort of image which has been flattened, we expect it to output in the end this vector of 10, and then having a number close to 1, basically depending on its on how sure it is about the incoming image, and then that being a number which is the highest from all of these. So let's see this. Okay, so what you can see here is the input. Let's draw a number. Let's draw the 3. What you can see here is the input from here. What you can see here are neurons which are connected with always all possible inputs it could have from the previous layer. So basically what's happening here is that they flattened this into an array, and then every neuron here is always connected to all possible inputs here, right? So what we call this line, and I can zoom out a little bit, here there is 300 neurons here, so all the way from neuron 1 to neuron 300. What we have here is a single layer in the neural network. So what stands is that every neuron is always connected with all possible inputs from the previous layer, and the previous layer in this case is the input. So all of these neurons are always connected with all possible inputs in this case, right? So this would be the first layer, and then we have another layer, which there is 100 neurons in this case, and then the same thing applies. So each one of these neurons is always connected with all of the neurons from the previous layer. And then all of this is then connected to the final layer, which has to have the size of 10, because that's how many classes we have. So the last layer basically has the same amount of neurons as what we want at the output, and that is 10. And that one is also always connected with all the previous neurons in the layer before it. Okay, so let's explain what these visualizations mean. So if we look at, let's say, if we look at this neuron, we can see that this line connecting it with some of the previous, with all of the previous neurons from the previous slide, they have different coloring, and especially this one that you can see between here and here has a strong correction. So the parameter of weight here is basically set to something large, while the parameters for all the rest are relatively low. The reason why this is shining is the sort of activation on that neuron. So that would be the accumulated signal in that neuron, and that would be something that we would see sending into future layers as well. So the output of that is 1.4. And so what we can see is that each of these neurons is firing with a different strength. So we can see, let's find one which has, okay. So this neuron has its own output is at 1.72. So this means that the y of this neuron sums into 1.72, and all the inputs, all the x, y, w, y are basically all the numbers in this previous in this previous layer. So how bright every one of these pixels sort of is, multiplied by how bright every one of these connections is. So this is what it means that we have xi multiplied by wi. Okay, and this is all the magic that is in there. Somewhere in these weights, in the connection strengths, there is encoded the capacity to recognize what a 3 is, and then being able to actually identify it as a 3. So how this was trained, so how basically we figured out what the correct weights are supposed to be, so what the correct strengths of these connections are supposed to be, we will talk about that later in the class. But for now, let's just try some other numbers. Okay, yeah, this is a good one, because what you can see here is that it's hard to actually guess for the model. So its first guess is 3. So I was saying a little bit in the in talking about the one-hot vector representation, in that this allows us to get an output with predictions for each of these classes. So basically what it means is that this neural network, which is here, thinks that this image is 0 with the -1, not probability, but the stronger this number is, the higher its confidence is. So with very low confidence, it's 1, so it's not 1. Not 0, I mean. With minus 0.5 confidence of it being 1, with minus 0.79 confidence of being 2, with 0.31 as a score for confidence for the 3, and you can see that it's maximal. So out of these numbers, 3 is actually the one that is firing the highest. 4 is some negative again, 5 is minus 0.08, almost invisible, and then 7 is actually 0.30. So it's very close between these two numbers, 0.31 and 0.30, but this model thinks that it's either 3 or 7, and maybe with like some number which is still, well, it's around 0, which is still better than all of these negatives. So it still thinks that it could be also 5. It is pretty sure that it's not 9 or it's not 8, and yeah. So I don't know if we can like make it more 3. It will be now it's a digital 3. So yeah, now it becomes way more confident that this is a 3 actually, and no longer a 7, which has some really low score. Okay, so I guess we can also illustrate that if we give it some nonsense here, something that it was not trained on. So for example, it was trained on numbers which are kind of really nicely centered in here, so it doesn't know how to read this 0, so it thinks it's all sorts of things. Basically, it's not sure about any of them. Well, it's pretty sure about a lot of them actually, but it's wrong about all of them. And if we give it some nonsensical image that it was not trained on, it doesn't know what to do with it. And well, this sort of illustrates that this model was trained on just on some data. So if I give it something new, basically what it thinks about it is it tries to explain it in the terms of what it knows. So in these numbers. Okay, if I give it some, yeah, this is a 0. I guess this is closest to 0 maybe from what it knows, or somewhere around 8 as well, maybe. Okay. So, right, so this was like a visualization of what we just went through in the class. If I slightly go back into just showing single neuron, so this yi is, let's make this a normal 3 again, semi-normal 3 again, wait, can do better. Okay, so the strength of this pixel, how bright it is basically, corresponds to how bright this y is, and then how strong these W's are, so how strong these connections are, is visualized by how strong these lines are, like how brightly they are lit. So it's really hard to actually like look at this and then trace it here and then understand it, because there is a lot of linear algebra happening there, and so we cannot really understand this by just looking at the different neuron weights. But you can kind of at least have an understanding of what's happening there. Okay. Right, and so maybe also to just illustrate, then we will have a whole layer of these. So yeah, if I go back into this case, I can illustrate that we will have a whole layer of neurons here, which will be the size of 300, as was in the example. We can have a whole layer here, which is the size of 100, which is the size of the example. And then we will have a last layer, which somehow has to mimic the last sort of the outputs that we want to give it. So it has to have size 10. Okay. So yeah, this is a kind of just restating of what I was already saying there. These are the model predictions. This is the strength of the connections. So the strength of the parameter, W, whatever this number is. And then how much each of these neurons are firing is how brightly lit they are. Okay. To sort of illustrate that, sure, this was a synthetic task. I mean, MNIST is a real world dataset, but it's a dataset from 1995. So there are some there are better models that can work with it much better than what I was showing right now. But the task itself, so classification, is not just something that can be used as a illustration why neural networks are interesting. It's something that can be actually used in real research as well. So here is an example of pattern recognition applied to seismic signals of the Jaima volcano in Chile. And so here they have some like a map of where this volcano is, and there are different types of sort of events happening there. And so they are all encoded. So I don't remember what these mean, but I think TR meant tremor, so this means that the volcano is shaking. VT might have been something like volcanotectonic, so this means some volcanic event. Other are people walking around the measuring station, and so we want to disregard that. And I don't remember what all of the other were as well. However, the task here is sort of very similar, because you again have some classes. So instead of having 0 all the way to 9, you have these LPs, TRs, VTs, whatever you labeled the data with. And these classes are represented with their own images. So this is like a spectrogram representation of this signal. And just by looking at these, you as a human being can recognize that, okay, all the images that have very low frequencies here will probably be this class. All images that, I mean, like only this class has something in these frequencies, right? So you should be able to tell the difference between these images. And the same way, a neural network, if you train it with these images, will probably be also able to just learn what is the difference between these images. So on a synthesis task as the MNIST, we saw that we can just like input in some letter or numbers, and it will classify it correctly, more or less, or get confused about them. In here, we can also kind of use the same models to classify these images as these labels. So just by the way, you would have to use some much more complicated neural networks to get really decent results here. And we will get into what it means to have more complicated neural network models. But in theory, you could just plug whatever you had here with these images. So I think the only problem would be that you would have a lot of connections here, because you are connecting everything with everything. So the first layer of neurons would be connected with all the pixels. And let's say that this is, I don't know, 200 by 200 pixel image. It's a lot of connections. So it would be quite hard for the model to train, and then also to learn something in there. Okay, so let's have a second pause. And then after that, after the pause, let's get back into how can we actually figure out what the weights should be. So how can we train a neural network? Okay, guys. So let's continue. I guess I want to start with saying that I appreciate that a lot of this might seem very abstract and conceptual, and so it might be quite difficult to understand all of these models, how they how the neurons fit into that, how can you actually calculate the weights that are being propagated through this neural network. And so I guess as a part of this, I will explain it again on a very on quite small example, and that will the example will be part of today's homework. And so the today's homework will consist of working with a single single neuron model. So not a full neural network, but just a single neuron. And so we will be manually finding the best weights to identify an image. So essentially this means that we will be training the model somehow. But don't really worry, because this will be just 2x2 pixel image, and there are just four weights to figure out in this case. And so also I think on this smaller scale example, you can probably get some better understanding of how the larger models work as well. Okay, so what we have is a 2x2 pixel image as an output. So this is corresponding, this is supposed to represent a 2x2 image of horizontal lines, let's say this, and then of vertical lines, let's say this. And so we want to use a single neuron as a model to distinguish between these two classes. So for this neuron, we will live in a world where the only thing that can come are images from this class, so which look like this, and then images that look like this. And the task that we want to train the model that will be plugged to this is to label these images with a number very close to 0, and then label these images with a number very close to 1. Okay, and so what that means is that we have some sort of model here with one single neuron with 4 weights to figure out, and then 4 inputs connected here. And these inputs are basically just the 2 types of images that we had there flattened into this is the first top left pixel, which will be here, then the second one, which will be here, and then we are basically scanning line by line. So here will be the third one, and then here will be the fourth one. And this is connected with 4 connections with the single neuron unit, which is here. There some magic happens, and then we output this here. And so to talk a little bit about the magic that's happening here, we will have a function. So instead of the sigmoid function that I was briefly talking about at the start of this class, we will have a simple function which lets through any positive numbers. So basically, how you can also think about it in terms of programming, for example, this would be a function which returns like the either whatever the number is, or 0 if it's some negative number. So it will, looking at the plot of this function, it will always let through anything that's positive in the same kind of number, whatever came in that will go out. But if it's negative, it will just leave it at 0. Okay, so this is just like just a bonus. This we call these functions, whatever is happening here, as activation functions. The activation function in this case, used in this case, this one is called ReLU, rectified linear unit. And actually, ReLUs are used quite often in models because they work well. But this is not like this will not really make it complicated for us to figure out these numbers. So this is just an explanation of what's happening here. But I guess the more complicated thing that will happen is what's happening here between. So how do these inputs get weighed by these values? And that's happening sort of here. We have to weigh in all the incoming signals. And so that means that x1 is multiplied by w1, x2 would be multiplied by w2, etc. And we have to weigh them, so this means the multiplication, and then we also have to accumulate them. So that means we are summing them before they make it into the function f, before they get into the sort of summa. So what's happening is that this formula that will be used, so sum across all the possible inputs and always multiply that input with its corresponding weight. And so if we just rewrite it, it's basically we get this formula. And so this is relatively short because we have just 4 weights and 4 inputs. But you can imagine if we had 784 or whatever inputs here, this line would be much longer, right? But in this case, note that all of these input values here are something that is fixed. Basically, that is determined by whatever the image will be that we see. But all of these wy, so all of these weights, is something that we will have to figure out. So we can set all of them to 0, for example, but then it will not work. But we can also set them to 1 all, and probably it will still not work. But we can figure out some nice combination, like 0.5 somewhere and something else, and then they will start working, right? So to connect this model, which we had here, and by the way, this is the same model, and I just draw it twice to illustrate that we can have 2 different inputs. We can plug them to 2 possible classes that we want to have in our dataset. So we want to have images of horizontal lines, which means these 2 pixels are dead, or we have images of vertical lines where these 2 pixels are dead. I guess I'm telling dead, but you can say like white and black, and then you can say that this value would be something around 1 maybe, and then this value would be something around 0. Okay, and so in these images, these weights, the W1 to 4, are the same for both cases, while the X1 to 4 are different for these 2 cases. So this is because the X1 to X4 are supposed to be representing the inputs, and so they take on whatever the value is coming in here. And the output here, the epsilon, or the y, is supposed to be as close to the label that we are designating to this class as possible. So if I rewrite all of this, the task is to, this is the what we can see here is the formula that's happening here inside the neuron. So you get all the inputs, all the x, y, w, y, summed together, and then you have the function applied to it, which is here, and the function is just minimal of this number and 0, and then this should evaluate into a number which I want to be 0, or as close to 0 as possible. So I think in this case it's possible to figure out numbers here that will make it exactly 0, and then in the other case, in the second class, so in this case, it will make it, it would come to a number which is very close or exactly 1. So this is a synthetic example, so it will be possible to figure out everything perfectly. Normally, we will have some number like which is close to that number, not exactly the same. Okay, so on if I substitute these x1 with the values for the pixels, and we have been saying that maybe these are 1 and then maybe these are 0, this is what would happen, that we get basically actually quite simple formulas, right? We have one formula with a lot of zeros, which means that we can actually ignore them, and then we have another formula with zeros somewhere else. And so the task in this case, it's still the homework, right? the task in this case becomes figuring out the numbers for the weights, which would make it evaluate into the number I want. Okay, so to sort of summarize it, this is our dataset. We can imagine that there are many more of the same classes. Maybe some are, I guess, slightly grayer or something, and then maybe some of them are some slightly less white and slightly more gray or something. But we can also say that there are just two samples in this dataset, and then we want these horizontal lines labeled as 0 and these vertical lines labeled as 1. Okay. So what this boils down into when we collapse these two images into these two lines is that we have these two formulas that we want to kind of figure out the weights for. Okay, and so to restate it, the task becomes to manually find the values for W1 to W4, which would do the classification between these two images, aka create a horizontal/vertical classifier. So some of you might already see what the solution is here already, but I think this is more like a illustration that should explain how a single neuron would actually be trained. Okay. So a bonus question, which is maybe also just to make you think a little bit about this task, is to think if this would work well with some new types of images. So the weights that you set here, sort of maybe try them for these images and then think about what would happen as an answer. Oh yeah, these are the same, but yeah, imagine that there is something else here as well. Imagine what would happen for these images and how if that answer that the model is giving you, so this number, if it's something that you are expecting it to give you. Or what would be the best possible solution there, maybe. Okay. So, right. What we were doing right now was manually training a neural network. So there is another comics. Oh, hey, you organized your photo archive. Yeah, I trained a neural net to sort the unlabeled photos into categories. Whoa, nice work. Engineering tip, when you do a task by hand, you can technically say you trained a neural network to do it. Okay, and so what we have been just doing in the homework was basically trying to find the best parameters to have this one single neuron work the best for this dataset, so to classify it. Well, what we were doing was basically training a neural network. So this brings us to the last section of today's class, and that is the topic of training. So how can we actually find the best parameters? Well, manually is one case, but it is relatively tedious. I mean, your homework is easy because there are just 4 numbers in there. But what if you have the models that we shown before, where there are maybe over 800 connections in the first layer only, and then way more connections in later layers as well. Basically, that becomes impossible to manually figure out. So the answer is automatically. We can try something like brute force, maybe just basically guessing all the WYs randomly, and then repeat this over and over and over again, and then just keep the model which was working the best. And actually this would work, but it would take ages, because like the exploration space for all the possible values for WY, where they can go from like somewhere some minus infinity to plus infinity, even though if they are somehow normalized and they go from -1 to 1, still it would be really difficult to figure out what the best solution is there. And so the answer is to go at this with some very smart algorithm. So again, automatically. So the smart algorithm I'm talking about is called gradient descent. And I will use another sort of metaphor to illustrate it. So imagine you are in a landscape, so in this bizarre landscape here, and then you want to, well, not climb a mountain, but find the deepest hole. I think climbing a mountain would work better in a metaphor, but that would not be called gradient descent, but gradient ascent, and so it doesn't then work with the whole minimization of error and everything. So let's just change it into finding the deepest hole. And there is a twist. It's also really foggy, and so you can only check your near surroundings. So if you are standing here, you don't know, you cannot really see that, hey, there is the hill. You only can see what is the slope around you. And so the approach there, which is kind of corresponding to this gradient descent algorithm, is that we start somewhere, and then we check around and then find the direction in which there is the most descending slope. So in terms of mathematics, this would be called finding like a gradient and finding the, which is something which is done by deriving the function of this landscape that we stand on and getting the value or values at the position that we are here, that we are at, and then getting the value of the most descending slope. Okay, and so we take that, we step in some amount of, like we jump some amount of steps, and then check again. And so we repeat this over and over, and then eventually we end up in like in a hole, in some minimum, right? Okay. Well, this has a small problem, especially on this image, right? It's that depending on where we start, with this method, we can end up in some hole, but this hole might not be the most optimal hole at all, not the most deepest one. So what this means is basically, or what this is called as, is getting stuck in a local minimum. So this is a minimum, like the minimal point in the landscape, but not the best minimum, but just just the one that we found. So this is called local minimum, and this would be called global minimum. And the problem really is that we cannot really check the whole landscape. So just beyond here, beyond another kind of hill, there might be even better minimum there, and so we don't really know how to check that one, or even how to jump from here to here with this method. So this is slightly beyond the current lesson and beyond this metaphor as well. There are some ways how to get around this, how to get around getting stuck in local minimums. And that would, for example, be that you can just repeat this over and over, and then with always starting at a different position. So you basically just have this initial point from everywhere, and then and then eventually one of them will end up here, and then actually end up in the best solution. But again, this is just sort of like pushing the problem forward slightly, because you still can fail with this as well. So what in the world am I talking about when this comes into a landscape and me finding the best hole or something? Well, the landscape, this thing, is a function, right? So this is a function which corresponds to a error, and so these axes, these different parameters for this landscape, are different values for different parameters that we can set. And so basically this means finding the best hole means I am finding the best location inside this 3D image where I am sort of what is the position, what are the x and y parameters to get the best z, or the smallest z in this case. And so this is this landscape sort of corresponds to an error, and I'm trying to minimize it, is what I'm saying. Okay, so let's bring this into a simpler example, which is basically just working with a 2D plot of a function. Let's somehow imagine that this curved function would be the error function for us, for our model, and this w is the one parameter we are setting, and then this function is basically how what is the error at that parameter. And so if we are at current position, if we set the network with this parameter at this position, the answers that we will be getting will be basically this distant from what we want to answer, right? So this would be the error. Well, gradient descent, we can, in gradient descent, we basically check the gradient, which is sort of the tangent, which can be visualized as tangent on a 2D plot, which will give us a number which says the slope of this tangent. So it will tell us if it's either descending to the left or if it's descending to the right. So one of these tangents has a positive slope, meaning that this line goes to the, has a positive slope. And so the direction I should take in the next step, if I want to find the best solution, the hole here, would be to go to the left somehow, some distance into the left. Well, if instead I were here, the slope of this other tangent line would be negative, meaning that this points to the right, meaning that the direction I should take would be to the right. And so saying left and right, it's not really mathematical. So in terms of this plot, this means maybe the direction of jumping to the left would be -1, and then the direction of jumping to the right would be +1. And this is a simplified case, but the formula here would say that if I'm in a current position here for the parameter W, so this current position is a W, and then I take a step of some size, this is some parameter that we can sort of change later, we would go into the direction of whatever this evaluates as, so either -1 or +1, and then take that sized step in this direction. So this means in this first iteration, we started here, we checked the tangent, which tells us, okay, we should jump to the left. I will update it. Maybe the step size is quite large, so it will jump us all the way to the here, and we will get the next position. And this is a iterative algorithm, so basically we repeat the same computation here, this same one computation here. And so in this next position, this becomes the next current position, and we jump from there, again checking the tangent, basically where is the slope turning to, and we will jump there, and then finally there. So this is a iterative algorithm which will eventually find the local minimum. You can imagine if there was another kind of better solution here, we wouldn't really find it because we are already in this one hill. You can, So just to restate, this function is a function of an error, and the parameter v, so the position that we are changing on this axis, is the parameter we are trying out. So we are trying to, okay, what if we set the parameter here? Well, the error is quite high. Let's go here. What if we tried here? Well, the error is still quite high. Okay, and so we end up all the way to the local minimum. So I guess the takeaway message in this case is that this is a special algorithm where we can get this slope as a derivation. So we can actually calculate the gradient, meaning we can figure out where the best next step would be, in which direction. Okay. Well, what about neural networks? We somehow want to have the same iterative formula here, right? So we have some current weights, all of these, and we want to update them somehow in a way that the next weights will actually give us better error. Well, for that, we somehow need to, this is the current prediction, and this is what it should be. So this is the, I guess we can call this the optimal version. This would be the bottom of the hill. This would be the hole, I guess, and this would be what our current position is at. And so we want to change these parameters to change this to be close to that. Well, so mathematically what this means is that we are comparing these two numbers, y label and y prediction, in the way that we can say that this is the error, the difference, well, some difference. There will be different types of differences. We will talk about that in later parts of the class anyway, but let's just say this in a simplified manner, where the difference is basically the just y prediction minus y label. And so this is some indication that tells us how far the error is, or like how far we are off with our current settings. Well, the really nice way, or really nice property of neural networks is that all of the calculations in one single neuron are differentiable. So that means we can derive them and get a gradient, which will tell us in which direction we should move to minimize the error. So this is something that is true of one neuron, but it's also true of the whole neural network. What happens there is basically that we are layer by layer, well, sort of neuron by neuron, checking what the prediction should be with regards to what the prediction is right now, and then kind of adjusting the weights accordingly. And so this is a simplified formula because it's more or less like a pseudo code of the formula. We still do have some update to the current weights in a direction, which is something that we get from the gradient, times some step size. And then this step size is something that we are probably adjusting over the run. It's called the learning rate as well. And then this is something that will influence how much we change or how much we trust the gradient to change our parameters, to change these weights. And so this is something that will be changed in the next weight. And this is something that we can sort of do again and again, repeat for one, for all the data, and also b, for repeated amounts of times. Okay. So what this means is we can iterate this algorithm to get some newer and newer values for weights, and then over time get closer and closer to the right solution. Well, to the solution which has a better error, so something which is closer to the label. Okay. So calculating the predictions, so going from the start of the whatever model into the predictions is called forward pass, and then calculating the update for the weights, so going from this prediction and the error here is called the backwards pass. Okay. So stepping kind of more away to see the bigger picture. Well, with larger neural networks, we repeat the same process. We have a forward pass going all the way here, and then we check the error which is happening at the last layer. We adjust the weights in the last layer, and then we can kind of see the error which is happening between this layer and the last one, adjust these weights, then the same, sort of check the error which is happening between the first and the second layer, adjust these weights, and then all of this has been done with like one data sample. And so we updated these weights with a forward pass, getting the predictions, and then backward pass, getting or updating the weights with some gradient. The really lucky point there is that all of this is differentiable, which means that all of this is possible. Without this, we would have to actually just have some brute force algorithm and try to guess all of these parameters, or have some other different ways. But the reason that we can differentiate the formulas here means that we can get this relatively fast and simple algorithm, which is gradient descent, to update these. Okay, so we repeat this process of going forward and backward during training, and then for all the data that we are feeding this with, and then we call these iterations epochs. So later when we will look at the code, there will be some, we will touch upon this because we will be training the model for several epochs to see how it's changing over time. Okay, well, so this is the end of the lecture, or the theoretical lecture at least, and then in the practical section we will learn about how to write all of this that we just talked about in theory. I guess all of this in theory maybe looks quite complicated and convoluted, and especially if you are hearing it for the first time, it maybe makes no sense. But then in the code, it actually is relatively easy to use, relatively easy to even build, and then practically we will see that it sort of just works. And for example, you will not have to program your own gradient descent algorithm. You can just use it. But it's still useful to know that something like that exists, and that it works in the way that we sort of described it before. Okay, so I will almost end today's lecture. When we are having the class, we will go over the practicum, in which we will build a fully connected neural network with Keras. So we will recreate what we learned about in this class. Basically, yeah, the motivation there is to finally build a model, or finally create something that we just talked about in theory and actually write it out into the code. And then also just to show you that it's really actually quite simple to write up and then to use. Okay. In practicum, we will start with these inside this notebook. You can already check it out if you want, but we will go step by step, almost like line by line in the class itself. So, but feel free to look at it. There is a solution there as well, so you will sort of know what's about to happen. Well, so the contents of the next class will be in modeling a artificial visual system, which is something that has given an inspiration to using convolutions. So in adding convolutional layers to our neuron networks. Also in explaining what this means, what this does with the incoming images, how does it translate them, and yeah, so what are kind of the byproducts of doing that. We will talk about a model called AlexNet, which is a famous model from 2012, and then also on a new dataset called ImageNet, where we will illustrate what these more powerful models, the convolutional neural networks, are capable of. And in practicum, we will try to load some of these models and then use them for something. Okay, just a short repetition. Your homeworks is to manually find values for these 4 parameters in order to differentiate between these 2 types of images. Yeah, more details are in the slides. Find that section there. And so I think I will make the submission through the weekly quiz, and so please answer the values there. Okay, and so this is the end of today's class. I hope it was understandable. I will repeat it again. Don't worry if you don't get all the details. What we are about is maybe getting the concepts, and then from there we will move on into later classes where we will start using those concepts, and maybe some of those topics I mentioned in this today's class will start sort of making up a bigger picture and will start making sense. Okay, so with that, goodbye.